Hello and howdy, ladies and gentlemen, and welcome back to more of the Hypatia contest put out by the University of Waterloo, the Hypatia from 2007. We are up to question number 4, which happens to be the last question. In the diagram, 4 circles of radius 1 with centers P, Q, R, and S are tangent to one another and to the sides of triangle ABC as shown. Okay. So, radius of 1, and whenever I see circles tangent to things, I connect radii up to those tangent lines, because it always makes a right angle, and that's usually the trick for some of these questions. So A part, determine the size of each of the angles in triangle PQS. So notice that P and Q circles don't actually touch, so that might be a bit of a challenge. Of course, explain how you obtained your answer. You're going to have that just about everywhere. B part, I'm choosing to read everything just because with question 4 can sometimes be, I find it's more connected than, say, previous questions, you'll often have to use your answer in B part to do C part. So sometimes it's a good idea on question 4, if you don't have an obvious idea of where they're going, to read A, B, and C, because it can give you some direction. As I'm working out these angles in A part, am I also noticing maybe how to get lengths for B part or whatever it is, that sort of thing. Okay, so, with questions, or all the questions, it can be a good idea sometimes to read them, but I find especially for question 4 or the last few questions on a Euclid, it's a good idea to read everything, especially if they're introducing a brand new concept, like, this is a Franklin sequence and that sort of thing. Anyway, let's get back to the question. So, we read A part, determine each of the angles. B, determine the length of each side. Hey, that's pretty nifty. Called that. So we need the length of each side for ABC. Maybe we'll have to find the area next. And, C part is a little more involved. The radius of the circle with center R is decreased so that the circle with center R remains tangent to BC. Okay. So we sort of shrink it down here. So the center R obviously doesn't stay where it is. The R moves with the circle. Circle with center R remains tangent to BC. Okay. The circle with center R remains tangent to the other 3 circles. So if it shrinks, I guess Q and S sort of have to roll into position as well, so they're still tangent. And the circle with center P becomes tangent to the other 3 circles, so P sort of rolls into place and touches Q and S and R as well. This changes the size and shape of ABC because it remains tangent to everything. Determine R, the new radius of the circle with center R. I feel like with C, as long as I set up the picture, it won't be that bad. But it doesn't appear to really be connected to A and B. Although maybe with this new position, we'll have to figure out the angles for PQS again and go from there. I don't know. I think it's pretty. I think I can definitely do A and B. C, we'll get to that one. But let's talk about some angles here. We'll get a fresh piece of paper for our notepad. So I don't think I need the. I have no information about A, B, C. So I think I can ignore them safely for A part. I don't know whether or not that's going to be wise. We'll draw them a little bigger. And then P was tangent to both of these. Okay, that's actually not that bad in my opinion. P, R, S. Okay. So, I want each of the angles in this triangle. Well, let's draw the triangle. So, the nice thing about Q, R, and S, so each of these guys, if we just want to talk for a moment, they're all tangent to BC. So they're all distance 1 away. So QS is parallel to BC, and QR is parallel to BC. So they all lie on a line. Okay, not so bad. PS is going to connect up right through this point of tangency. And PQ is going to be up here. Okay. So it's not immediately obvious what we should be doing here, but if I get, say, another color, let's go with this yellow here, and connect up, always connect up your radii to your points of tangency. We get ones here, we'll go back to the blue, we get ones here, and ones here, and ones here, and ones, well, you know, we've got a bit of a gap here, but we don't have to figure out side lengths for PQRS, so we should be fine. Okay, now notice that so by connecting all the centers, we see PRS is equilateral. How do you know it's equilateral? We don't know the angles. Yeah, but we know that it's 2, 2, and 2. So what does this tell me? It tells me angle PRS is equal to angle PSR is equal to angle RPS, and all these guys are 60 degrees. So hey, we've got an angle. Not only that, we've got this angle here and this angle here, and they're all 60. Okay. So 60 degrees, but if that's 60 degrees, and as I already said, QS is a straight line going through R, which I guess we'll have to prove now, we'll get 120 here. So this is now isosceles with length 2. We can get each of these remaining angles, and we're done. So, since QR, QS, and RS are seen to be distance 1 away from BC, we conclude they are parallel to BC. So this is a nice result. You got two lines, and you know at two different points on one of the lines that its shortest distance, which will have to be a perpendicular line, is the same distance away in both cases. They have to be parallel lines. Okay? If they weren't parallel, they'd intersect, and so the lengths would decrease in some fashion. Or the shortest distance would decrease, because it would have to be getting closer to 0 in one direction. Okay, so that's a nice little result. So they're parallel to BC. From this, we can conclude QS contains R. Therefore, QRP plus SRP is 180 degrees. And that tells me QRP is 120 degrees. Because I know SRP, it's this one right here. First one there. So we get 120. Now notice triangle PRQ is isosceles. So angle PQR is equal to angle QR, or is equal to angle QPR, which is 180 degrees minus the 120 degrees all over 2. So it's going to be 30 degrees. So 30 degrees, and hey, we've got a 30, 60, 90 triangle. So we'll just finish this off. So the angles that we cared about, the ones that they want us to find, this one right here, PQR, this one right here, and finally, angle QPS is equal to angle QPR plus angle SPR, which is 30 degrees plus 60 degrees equals 90 degrees. And you put a therefore statement, and, get all the angles together. I'm just boxing them up so it's clear that I do have all the angles calculated here. Okay. So it's a nice little 30, 60, 90 triangle. And other things that I've noticed, BC is perpendicular, or sorry, not perpendicular, is parallel to one of the sides of this triangle. And I'm fairly certain AC and AB are going to be as well, and that might help me figure out some side lengths. Anyway. So, B part, we said we needed to figure out the side lengths of our triangle. So I will draw my circles again first, and then draw the triangle around it, rather than draw the triangle and trying to fit in the circles. There we go. We'll put that one on top, and then we just have this extra one sitting out here. I may need to draw this bigger. We'll see. A, B, C, Q, R, S, and P. Okay. What do we want to do? Well, I'm going to connect some right angles up here, right angle here, right angle, right angle, right angle, and right angle. So yeah, everything's one away. I'll draw in my triangle again. And this is a right angle, and it's 60 and 30. Okay. Where do we go from here? Well, so we get a rectangle here, well, actually a square here, rectangle, so you'll get 2. And then we get this extra length here, which we can probably calculate in some fashion. We're going to call it X. We get a 2 here, a 2 here, and then there's this guy left over, which is Y. And so similar to what we stated in A, we see P and S are one away from AC, therefore PS parallel to AC, and likewise PQ is parallel to AB. So, and we already know that QS is parallel to BC. So, these guys, thus ABC is similar to PQS. If you wanted to explain this a bit more, if you weren't satisfied with that, you notice that the PS, we can sort of extend him out here. And so, this angle here is going to be the same as this angle here because these are parallel. And then that's going to be the same as this angle here because these two are parallel. So you get the same angle here, you get the same angle here, you get the same angle here. And you can get similarity. If you wanted to say that, by all means, maybe I'll come back and state that explicitly, but I think we have bigger fish to fry in this question. Okay? So this triangle, similar to this triangle. Not congruent, obviously, but similar. Okay, what to do here? So you'd say something by looking at rectangles, and also this one here isn't 2, I just realized, because he's that large gap. Well, he is 2 root 3. I'll talk about that in a moment. By looking at rectangles, we see AB is equal to 1 plus PQ plus a certain amount X. BC is equal to, I don't want to, how am I going to say this? I know what I mean, but that doesn't mean it necessarily translates properly. Okay, so first let me show that, so since PQR is right angled, PQ squared is equal to QS squared plus minus QS squared minus SP squared. So that's going to be 4 squared minus 2 squared. This is going to be 12, so PQ is equal to 2 root 3. Okay. I think I'm going to have to name these perpendiculars, which I was really trying to avoid. D, E, F, G, H, I, J. D, E, F, G, H, I, J. Okay. What else? Suppose I'm going to have to draw up these lengths here. Right angle, same length and same radius. Yeah, those there. So let's note some things. BG is equal to BH, since triangle BQG is congruent to triangle BQH by side, angle side, or because it's a right angle and I know these two side lengths, doesn't really matter. Same, we know that CD is equal to CJ. Since CSD is congruent to CSJ, again, side angle side would do just fine here. Actually, I'm just going to say it's Pythagoras, because I believe side angle side has to have the angle. No. Anyway, Pythagoras. Pythagoras. Okay. So I'm going to say let BG equal X and let CD equal Y. Okay, so now we can say things like by right angle triangle or by rectangles. You see that AB is 1 plus 2 root 3 plus X. BC is X plus 2 plus 2 plus Y. And CA is Y plus 2 plus 1. Okay, I did remember that correctly, right? 1, 2 root 3 X, X 2, 2, Y, Y 2, 1. Okay. So now we could say, since it's a 30, 60, 90 triangle, or because it's right angled, we could set up equations. We could set up a b squared plus ca squared is equal to bc squared. That would be fine. But by similarity of ABC and PQS, we note that AC over 2 is got to be the same thing as BC over 4. And this is also technically AB over 2 root 3, although I don't think I need that one particularly. Okay, so BC is twice AC. X plus 4 plus Y is equal to twice Y plus 3. And that's 2Y plus 6. So from there, cancel a Y. We'll get Y plus 6 is X plus 4. Or X is equal to Y plus 2. Yeah. And from there, what do we do now? So what? I guess I should plug it into. Yeah, I guess we have to use the other equation. So we'll move this over here. X equals Y plus 2. And now AB is going to be root 3 times AC. Well, that's 1 plus 2 root 3 plus X is equal to now root 3 times Y plus 3. And that's 1 plus 2 root 3 plus Y plus 2 is equal to root 3Y plus 3 root 3. Those guys will cancel and give a root 3 here. So Y plus 3 is equal to root 3Y plus root 3. How am I to use this information? Y minus root 3Y is equal to root 3 minus 3. We'll do it the other way. 3 minus root 3 is equal to root 3y minus y. Take out a root 3 over here, you'll get root 3 minus 1. Take out a y here, you'll get root 3 minus 1. Therefore, y is going to have to be root 3. X is going to have to be root 3 plus 2. And now I can tell you all these lengths. So AB was 1 plus 2 root 3 plus X. Well, now that's 1 plus 2 root 3 plus root 3 plus 2, or 3 root 3 plus 3. AC was y plus 2 plus 1, or 3 plus y. Well, now that's 3 plus root 3. And BC was x plus 2 plus 2 plus y. Now that's root 3 plus 2 plus 2 plus 2 plus root 3. And that's going to be 2 root 3 plus 6. Okay, and we can double check. Yes, twice AC is BC, so it all works out. And that's all we needed to show for B part. Determine the side length of each side, and I definitely explained how I got my answer. I don't think you needed to go back and justify the similarity of ABC other than by saying parallel lines. I think that's clear. Alright, now the C part, and this is the one where I think I need to draw up the picture quite well, so we're just going to reread it. The radius of the circle with center R is decreased so that circle with center R remains tangent to BC. Let's draw this as we go. I'm going to flip the page just because I feel like I'll need more space. So I'll make my BC quite big. So the radius is decreased. And they gave a name to the radius, didn't they? Maybe we'll make this a little bigger. But I think they called it little r. Double check. Yes, they called it little r here. Okay. So the circle with center R remains tangent to BC. Fine. The circle with center R remains tangent to the other 3 circles. And the circle with center P becomes tangent to the other 3 circles. So the other 2 circles, they're bigger, so their centers are up higher. Going to be a little something like this. Kind of looks like Hitchcock right now. There we go. And this one, we can draw it a little more smoothly. and then the other one comes in, and so it can't quite be this big. Other one, the one with P, comes in and touches them both as well. It looks like an egg, but it's fine. Okay. So there's P, there's S, there's capital R, and there's Q. Okay, now they're still tangent as we required. So QS still very much parallel to BC, it's just R doesn't lie on there anymore. So as I always try and do, I'm going to connect up centers. So we get 1 and a little r, 1 and a little r. I like that it's the same length here, a little r and a 1 here. And I can connect these up, why not? So we get side lengths 2. So we get 2 congruent triangles. I don't know whether or not we'll need them. And they say A, B, C changes the size and shape. I don't see how that's going to help me determine R, because I would need to recalculate some of these lengths for A, B, and C, and that requires knowing things like the length of P, S, which I do know. It seems like it's just encapsulated all here. I guess they probably said A, B, C changes shape just so that you really realize that you have to redraw the picture. Okay, what are we to do? We want to know R. We want to know little r. So, it's one unknown. I would guess we set up some sort of an equation here. Now, what to do? I feel drawn to drawing out QS just because I know it's parallel. And I'll even say QS is still, by the exact same logic that we had before, parallel to BC. It's just R isn't necessarily on it. Okay. By symmetry, PR is perpendicular to BC. P has got to be right above R, otherwise you would not be able to cram them in here. And I think it's clear that you say by symmetry in this case. So that means I get right angles here. I also get this length QS, which there's 2's here. Maybe I can figure out that length. And then what have we got here? So this distance in here is just 1 minus r, because these guys are 1. And if that's 1 minus r and this total distance is 1 plus r, then that leaves this guy here as 1. And I've got 2 right-angled triangles, both expressing this same length here. So I might say call the intersection T. Call this cuddly little fella T in here. Okay, so I think I can calculate QT in 2 different ways. So QT squared is equal to PQ squared minus PT squared. And you'd need to actually point out that PQ is 2. So 2 squared minus 1 squared, so it's 3 squared. Not 3 squared, it's just 3, which is root 3 squared. Okay. So 2, and this has got to be 1, because we've got 1 minus r and 1 plus r. Right? No. No, PT isn't 1. What am I talking about? I'm crazy. It's 2r. It's 2r. Right? 1 plus r minus 1 minus r. The 1s will cancel out. Yeah, you'll get... so this will be 4 minus 2r squared. Yeah. So I don't know what that is, but it's 4 minus 4r squared. Okay, so that's one way to get QT squared. We got another right angle triangle, and you should probably be saying things like RQT is right angle, but let's not waste our time right now. QT squared is also equal to RQ squared minus RT squared, and this is 1 plus R squared minus 1 minus R squared. A little less helpful, but then I can equate these and I'll get a quadratic in R and probably dismiss the negative answer, that sort of thing. So we get 1 plus 2R plus R squared minus 1 minus minus, so plus 2R minus an R squared. So it's going to have to be 4R, which is odd, but okay. Alright, so we've got 4 minus 4r squared is equal to 4r. Well, let's get rid of the 4, so 1 minus r squared is equal to r. I can rearrange this. R squared plus r minus 1 is equal to 0. Not going to be the easiest thing to factor, so when in doubt, quadratic formula. R is equal to negative 1 plus or minus square root of 1 squared minus 4ac all over 2a. So that's negative 1 over 2, and I know I set it upright because it's going to be 1 minus negative, so it's so plus 4, negative 1 plus or minus square root of 5 over 2, which is a fairly well-known number. It's the reciprocal of the golden ratio, and r is a length. So it is positive. So we're not going to do the negative 1 minus a root 5, because that's just going to make it a more negative number. Therefore, r is... I'll stylize it this way, root 5 minus 1 over 2. Okay, that actually didn't take that long once I saw the connection. So doing justifying that you can use Pythagoras, or justifying these lengths PT and RT, you might want to devote a little more time to that. But that actually wasn't so bad. I could imagine question 4 being harder if you didn't. I mean, I can't really justify why I wrote QS in, other than I'd used it for parallel arguments before. And maybe that's just the brilliance of the people making it up in question, the people making up the Hypatia. But I could see this one being a little harder if you hadn't seen that immediately and it hadn't turned out so well for me. But overall, I'd say it was a very nice, very relaxed question number 4. There was certainly geometry going on. We worked for our answers, but I never felt particularly stuck at any time, which I always am of the opinion that I should feel, where I am at in terms of doing contests, I should feel a little stuck on a 4, a bit more stuck on say a Euclid 10, that sort of stuff. But maybe it was just an easy contest. I liked the 2007 this year, and we're all done. 2007 Hypatia is gone. Up next will be the 2007 Euclid, and eventually the 2008 Hypatia. If you're looking for more Hypatias, of course, you can take a look at the 2006, 2005, and so on that I've already got posted up on my channel. But thank you guys for watching so much. Good luck on a future Hypatia, or really any future math contests, not even the Waterloo ones. There's plenty out there. And I will see you guys again in another video. Thanks for watching.